In later sections, we'll introduce a few more derivative properties and rules that allow us to find the derivatives of more complex functions. But we can build on the relatively simple rules that we've already established to tackle some slightly more complicated problems already. What that's going to require us to do in these next few examples is use rules of algebra to rewrite a given function in a way that matches the properties that we've established. For instance, in example 14, we'll start off by expanding this expression out. Multiplying these terms will give us 4x squared minus 8x minus 4x plus 8, and then combining some like terms will give us 4x squared minus 12x plus 8. Now what we have is a rewritten function, exactly equivalent to the original expression, but we can differentiate term by term and apply the power rule. So to find dt over dx, we'll differentiate 4x squared, which will give us 8x. We'll differentiate 12x, which will give us just 12, so we'll have minus 12. And then again, just to drop in this placeholder of plus 0 to see where that constant term disappeared to, meaning our derivative function will be 8x minus 12. In example 15, we can take this rational function, and since we have just a single term in the denominator, we can break it up as the sum of multiple fractions, meaning we could rewrite this as 3x to the fourth over x plus 2x cubed over x plus 1 over x. That works because now what we have are three simpler rational functions with a common denominator. We could add those together and get back to the function we started off with. Now we can apply a little bit of simplification here. 1x will reduce with 1x in the numerator in the first term. We'll cancel out 1x in the second term. And then 1 over x we could rewrite as x to the negative first power. And now we can apply the power rule again to our new function, which will be 3x cubed plus 2x squared plus x to the negative 1. So to find d over dx of m of x, we'll differentiate term by term to get 9x squared plus 4x minus x to the negative 2. In example 16, we have e to the negative 4 plus x. The derivative property that we have only works for e to the x. We have a more complicated expression in that exponent, so we can't apply that property directly. What we can do, though, is think back to some rules of algebra and consider if we had something like x squared times x cubed, we combine those by adding those two exponents together. So this would become x to the 2 plus 3 power, or x to the 5th power. And that rule can be generalized. If we have x to the n power times x to the n power, then that's equal to x to the n plus m power. And since those two statements are equivalent, we can move back and forth between that relationship in either direction, meaning we can break this up into e to the negative 4th times e to the x. Because according to that property, we would add those exponents together when we merge those factors to get back to the original function. Now, in order to find g prime of x, we're taking the derivative of e to the negative 4th times e to the x. It may not look like it, but e to the negative 4th is just a number because keep in mind e is a constant. It's about 2.78 raised to the negative 4th power, so that's really just a coefficient. We're taking the derivative there. So all we're doing is taking the derivative of e to the x. The derivative of e to the x is just e to the x. And now we can use that property of exponents to merge these two factors back together to get e to the negative fourth plus x. We took a lot of steps. Our end result looks the same as our initial result, but we did go through that process of taking the derivative. Sometimes with exponentials, though, we don't see any change because of that basic property where the derivative of e to the x is just the function itself.